hx ax vector, hy ay vector plus hz ez vector. Okay, so if you taking the dot product, okay, if you take the dot product e dot h, so then what you will get means ex hx, the respective term. Okay, this when you take a dot product would be the same. Okay, same direction element, it becomes 1. If you take a different direction element, it becomes 0. So then ey hy plus ez hz. Okay, ez hz. So now I am going to tell the effect of the condition, whatever coordinate system it may be. Okay, suppose I am telling uh, x-axis. Okay, the three-dimensional quantity is like this: x, y, z. Okay, x, y, z. Suppose I am feeding the input, sorry, signal from the transducer, feed it to the represent in a three-dimensional. Okay, so almost the signal plane, signal uniform plane will over to the x-axis. Okay, over to the x-axis, and it is the three-dimensional quantity. One of the coordinate system will be in x-axis, and other one is y-axis. Mostly the other coordinate will utilized for propagating of the signal. Okay, so mostly in the notations, okay, notations, we will use z-axis only in your transmission line and antenna system. Why means, okay, so most of the signal effect, okay, the dimension of the uniform plane will be utilized in x and y. Okay, x and y, and for propagation, okay, for movement, the z axis has been utilized. Okay, z axis has been utilized. So this is in schematic. Okay, so when I'm telling like this, so then x component becomes 0. Okay, so consider anyone, either x coordinate system or y coordinate system. So I can tell, since it is lying on x axis, the wave lies on x axis. Okay, so then Ex hx is equal to 0. Okay, Ex hx is equal to 0. If Ex hx is equal to 0, then above expression becomes like this. E dot h is equal to Ey hy plus Ez hz. Okay, Ez hz. So this is your first equation. Okay, this is your first equation. Now I am going to introduce another constant called intrinsic impedance. So what is the word called intrinsic? So the word intrinsic literally means that something internal property of any substance or any material or any other product. Okay, so each and everything have their own electric and magnetic property. Okay, so the intrinsic impedance, we know that the intrinsic impedance is denoted by the symbol eta. The intrinsic impedance is denoted by the symbol eta. Okay. So the intrinsic, we know that the intrinsic impedance is denoted by the symbol eta. So in last class, I have told you the definition for eta. It is nothing but it is nothing but the ratio of electric field and magnetic field. Okay, electric field and magnetic field. I am going to represent the equation in terms of the axis. Okay, axis. Please see, numerator you have the electric field, and denominator have the magnetic field. Yeah. So the numerator has the electric field and denominator has the magnetic field. Okay. So whenever the propagation factor comes in denominator, it will be in phase. Okay. So whenever the propagation factor in where? In z axis only. It is propagating along z direction. Okay, in z direction. So in other two directions, the signals are lying over. Okay, or lying over. So then, the one form of the equation like Ey by Hz. Okay, Ey by Hz. So if input is given at y of electric field, okay, then output you will get Hz. Okay, for magnetic field. It is in phase component, so it is positive term. If I am putting Z term in numerator, okay, if I am putting the Z term or Z suffix term in numerator, then it is the reverse. So that one you have to give like Ez divided by Hz, Hz Ey. Ey. Okay. So between Z and Y as the phase difference, so minus you have to introduce. Okay, minus you have to introduce. Now you equate this equation, then you will get Ey and the Ez in separate. Okay, so what is Ey expression? Ey is nothing but eta into Hz, just cross multiplied. Okay, similarly Ez. What is Ez? It is nothing but minus eta into Hy. Okay, eta into Hy. Now you substitute the condition into the first equation. So substitute in first equation, that is E dot H, which is equal to Ey dot Hy. Okay, Ey is nothing but eta into Hz. Okay, so Ey is nothing but eta into Hz into Hy. Plus, okay, plus Ez. So what is Ez? Ez is equal to minus eta into Hy. Okay, so minus Ez, instead of Ez, I am replacing as eta into Hy into Hz. So please see the first and second term, almost both are the same. So plus minus becomes 0. Okay. So then candle dot product of electric and magnetic field is equal to 0. Okay, the dot product between the electric field and the magnetic field is equal to 0. Or otherwise, I will give you the statement like this. This is a uniform plane wave. Okay, this is the uniform plane wave where electric and magnetic field are perpendicular to each other. Okay, so this is your first condition. This is for only dot product. So whenever dot product we are putting, it is somewhat equal to multiplication. Okay, multiplication of the two signal. So, but in the cross product, what we will do means it is a vector and identity of the cross product. Sorry, in matrix we will do some multiplication and some rules are there we will follow for expanding that matrix. Okay, let me go for the second case. Okay, let me go for the second case, that is cross product of E and H. Cross product of E and H. Cross product of E and H. So what we will do, we will have to take the cross product. We know the what is the vector notation of E and H. So in first row, what we will put the unit vector Ax, Ay, Az. Okay, E is equal to Ex, Ey, and Ez. Similarly, the third row is for magnetic field, that is Hx, Hy, and Hz. So now we expand this matrix and apply the conditions, and we will get the resultant cross product equation between E and H. Okay, let you expand this step. That is Ax vector into this is Ax, then you will cross multiply and the minus of that multiplied vector. That is Ey, Hz minus Ez, Hz. Okay, this is for the first unit vector, that is Ax. So when you go with the second unit vector, you have to put minus Ay. Okay, Ay. So then how you will expand? Ex, Hz minus Ez, Hx. Okay, and the third thing is that A is it. Okay, A is it. So for A is that how we will expand? It is nothing but Ex, Hy. Okay, Ex, Hy minus Hx, Ey. Okay, so I hope you have understood just the matrix multiplication. Just solve it. Okay, so we know the conditions like this. Since Ex and Hx is equal to 0, okay, since Ex and Hx is equal to 0, and also we know that eta is equal to Ey by Hz, and also it is equal to minus Ez by Hy. Okay, minus Ez divided by Hy. Okay, so now you apply in the above expression. So then what happens? So almost the second term and the third term get vanished. Okay, first second term and the third term get vanished. How? So we already told that Ex is equal to 0. Okay, Ex is equal to 0, and X is equal to 0. So this term get vanished. Similarly, here also 0 minus 0. This term also get vanished. So the only thing is that E cross H is equal to Ax vector into Ey dot Hz minus Ez dot Hy. So now you substitute instead of Ey and Ez from this expression. So then it becomes Ax. So how you write Ey? Ey is equal to eta into Hz. Into Hz is there. I will put square. Similarly, minus Ez is nothing but Ez is nothing but what, minus eta into Hy. Already minus is there. So it becomes this. That is eta into Hy 2 times is there. So this becomes like this. So now you take the common factor outside. So you will get the common factors like this. Ax, eta is a common factor. So Hz square plus Hy square. I will simply make it up H square. So since H square is equal to Hz square plus Hy square. Okay, Hy square. H square is equal to Hz square plus Hy square. Okay, Hz square plus square. Okay, which is equal to what? H square. Okay, so this is the nothing but it gives the direction in which the wave travels. Okay, so this gives the direction in which the wave travels. So the wave travels. Okay, so that is only deals with the cross product. The next term is nothing but the phase velocity and the group velocity. Let me see what is the relationship between phase velocity and group velocity. Okay, so let me go with the next topic called phase velocity. Phase velocity and group velocity. Okay. Phase velocity and group velocity. So what is meant by this wave packet? Okay, let me explain with help of the graphical notation. So consider x-axis is the time. Okay, consider the x-axis is your time, and y-axis is the function of the wave. Okay, the function of the wave. So it will be goes in the form of the packet, a cluster of packet or group of the packet like this. Okay, in the packet, the wave pulses of the signal will be generated. It have both the electric and magnetic field. Okay, it will be in the form of like this. Okay, the signal will be in the form of like this. So the signal will go with the different velocities. That I will tell what are the two types of velocities are there. So the inside term, which is nothing but Vp, it is nothing but a phase velocity, and outer thing is nothing but Vg is nothing but the group velocity. So this cluster, okay, this cluster is nothing but the wave packets. Wave packets. So what is meant by wave packets? The wave can be grouped, and such a group are called as the wave packets. So the wave packets are otherwise known as the wave guide. So it will be guide in a protected form of the electric and magnetic field. okay, of electric and magnetic field. So let I will give you the definition for the wave packet. A wave can be in the group. Okay, a wave can be in a group. Okay, so such a group of thing is nothing but a wave packet. Okay, wave packet. So let me come with the two important terminology. One is nothing but a phase velocity. Another one is nothing but a group velocity. Let me come with the phase velocity. Okay, the phase velocity is the velocity at which the phase of the wave propagate in free space. Okay, so that is called as phase velocity. Once again, I repeat for phase velocity. So the velocity, okay, so it is here velocity at which the phase of the wave, okay, the phase of the wave propagate in free space. Okay, propagate in free space. Okay, propagate in free space. Actually, it is a general formula. Please remember the formula. Okay, so it's not have separate derivations or anything. So it is denoted by the symbol Vp. Vp is equal to C whole divided by root of 1 minus omega p divided by omega c whole square. Okay, so C divided by root of 1 minus Wp divided by Wp the whole square. Okay, so this is nothing but the wave, the phase velocity is nothing but that is what? It is the cluster of the pulse signal inside the wave packet. So I can also define it as velocity per phase velocity beta. Okay, omega by beta. It is your phase velocity. Okay, phase velocity. So while we designing the antenna systems, okay, like a dipole antenna or halfway dipole or monopole antennas, and then array type of antennas, this type of phase velocity component is required. So with the help of these parameters only, we will design that entire structure. Okay, so please go to the second terminology called group velocity. Okay, group velocity. For group velocity, how did the statement can be given? Okay, it is a velocity. Okay, it is a velocity of propagation. It is a velocity of the propagation of a group. Okay, of a group of frequencies. Okay, of frequencies. Okay, it is the velocity of propagation of then how did the equation mathematically given? Okay, so please see this equation. Please see this equation. Velocity given like c divided by root of 1 minus omega p by omega. Okay, so the omega is nothing but an angular frequency, where omega p is nothing but a phase angular frequency. Okay, so whereas For group velocity, the formula will be given like this: Vg is equal to C into root of 1 minus omega p by omega t whole square. So this is nothing but your velocity. Phase group velocity and the phase velocity. So I can give the relationship between the phase velocity and the group velocity like this. So the phase velocity is equal to the twice of uh, the group velocity. Okay, so this is the difference of the phase velocity and the group velocity. Second part, we are mainly focused on the waveguide. Okay, waveguide. So once we detailedly study about waveguide, then we have to prefer for which type of transmission is. Okay. Actually, the same parameter we will come up with again wave propagation in lossless medium. Okay. Before that, we should know about what are polarization. Okay, polarization of the plane wave. Actually, what is meant by the word polarization? This you have studied in physics, and also you studied in basics of electronics also. Yes, so polarization of plane waves. So I will tell what is meant by polarization. From that, we will give a simple definition. It describes the time varying behavior, a time varying behavior of electric field intensity, time varying behavior of electric field intensity at a given point. Okay, at a given point. Okay, so it describes the time varying behavior of electric field intensity at a given point. Then only for electric field intensity? No, it also for the magnetic field intensity. Okay, both electric and magnetic field intensity. So then I will come up with a new definition, like it is defined as the orientation of the electric and magnetic field at time varying condition. Okay, so that is called as polarization. Okay, that is called as polarization. There are three different types of polarizations are there. It is a theory part only, it is not a derivation, it is a simple part. Okay, there are three types of polarization. Okay, so one is linear polarization. Okay, one is linear polarization. Second one is circular polarization. And the third one is elliptical polarization. Okay, linear polarization, circular polarization, and elliptical polarization. So let me see quickly about what is meant by linear polarization. So in linear polarization, the electric or E field in one direction. It not have the magnetic field. Okay, E is fixed in one direction. So then such type of polarization is nothing but a linear polarization. So whereas a circular polarization, sum of two linearly polarized. Okay, the sum of two linearly polarized wave with equal magnitude. Okay, Okay, the sum of two linearly polarized wave with equal magnitudes. Okay, the sum of two linearly polarized wave. That is the first type is linear. Okay, sum of two linearly polarized wave with the equal magnitude. That is called as a circular polarization. Okay, where the sum of two linearly polarized wave with different magnitudes. Okay, with different magnitudes. Then it is called as elliptical polarization, where E1 and E2 is not equal, whereas here E1 and E2 equal to equal. Only a single electric field will be there. So it will be like this. It will be only the propagation of the signal alone there. Okay, it's the E field. Whereas in circular polarization, suppose I am considering x-axis as E1 and y-axis as E2. Okay, so it have the equal polarization in all directions, equal amplitude. Whereas in elliptical, it not been an equal. So it have one major axis have one amplitude and the minor axis have the another amplitude like this. Okay, so it will be okay. So this is your major axis and this is your minor axis. So the dimension has been varied. So these are the types of polarization of the wave polarization. So in next class we will look into the wave propagation in lossless medium. So they have some values like attenuation constant, then phase velocity shifter, velocity wave or wave velocity. So these are the contents will be seen in next class in detail. For the two cases, one is for the general lossless medium, and secondly, we will see about the plane wave in a fixed space. I hope this concept is clear to you. If you are having any doubt, please clarify with me. So now I will call up for the register number for the attendance. Uh, number 1002.
Present, sir.